All right, let's get started. So basically, two announcements. The first, lab 5 was just uploaded, and so for lab 5, you do need to come to the lab, because you need to receive a signal from the TA, right? So because of the receive frequency of the RTL SDR that you have. So we cannot receive the the signal in the air. So we need to receive it from the generated signal of the TA's USRP. Okay, so I think we only have maybe a couple of labs that we need to really go to the lab. Other labs can be done at home. Okay, and secondly. So what is the second thing? I cannot remember. I cannot remember. I'll see if I remember. So basically, and all the by the way, can you see my announcement in the canvas? Okay, because I didn't receive any email if I send an announcement, just to make sure. So check the announcement. Normally, if I have any update, I will just update the announcement. Okay. All the videos are up to date for now. So I will make sure that I update the video as soon as possible. Okay. I think that'll be it for now. So any questions, comments? Okay, so if not, let's take a brief overview of our previous lecture. So basically, in our last lecture, we did an analysis of PLL, right? And to make sure how to choose the loop filter to make the error converges to 0 in the time domain, okay? And then we talk about the PLL in presence of modulation. So basically here, we focus on the DSP-SC signal, right? And see how we can apply PLL in the DSP-SC signals, okay? And let's see how we have done that. So basically here is a PLL that we have seen, right? And equivalently, so this is the figure of the PLL, right? And so basically here, when we do this analysis, so normally we convert it into the frequency domain, right? But here, because we need to do some kind of filter design, so we convert it to the Laplace domain, okay? And in the Laplace domain, so now we can basically write everything, as a polynomial, right? So which is much easier to analyze, okay? Yeah, can you hear my voice? It's kind of weird. A little bit? Okay. Yeah, I'll try. So I have a huge headache from last Wednesday. I have no idea what's going on. I've never had this kind of headache before. And then, so I'm getting better and worse. And this morning, I think I'm fully recovered. Yeah, but now I have like this kind of a little bit, faint feeling. So it's like so I'm standing on some cotton. It's kind of in a boat. Yeah, I have no idea what's happening. But I think another reason I don't have this pain is that so my gout came back. I have a gout attack this morning. You know what's gout? It's kind of something in your feet, right? So it's very painful, but I have medicine for that. So probably because my gout is back, then the pain coming, focus on my feet, and then my pain, my headache is getting better. Okay, so it's a kind of convert. I don't know. Yeah, just bear me a little bit if my voice I feel strange, right? So really feel like I'm on a boat. Okay. Anyway, so here we just analyze everything in the Laplace domain. Okay. Oh, by the way, for my video, right? So when you watch it, especially for whom you didn't come, so if you see anything weird in the video, this is because that I cut it, right? So I cut the I think in the previous very few lectures. So yeah, I made a few mistakes. So I cut the mistake out, right? Because I think that is confusing. Okay, I think when I watch it back, I think everything goes relatively smoothly. But if you see something weird going on, yeah, that's the reason. Okay. Yeah, let me know if you have any questions. Okay, and here are the two cases we considered, right? So in the last lecture, we focused on this case, right? So when the loop filter is just a constant, we can show it doesn't work in general, right? It works when we have a phase offset, right, only. But if we have a frequency offset, it will not work. Okay, what did work is this form, right? So if the loop filter is a constant plus sorry. I remember the second announcement. So I'll be out on Wednesday. So there will be no class on Wednesday. However, so I will record a video lecture on Wednesday, but I cannot upload that on Wednesday. I have to travel. So what I'll do is as follows. So basically, I will record it probably during this weekend. Do you remember? So we skipped one more lecture before, okay? So basically what I'll do is that I'll record 2 lectures, okay? Hopefully you can watch it during the spring break. So it's only like 100 minutes, right? But if you cannot, maybe you can watch it on the Monday morning when we came back. So I'll record 2 lectures, okay? And then, so I think, yeah, we'll be on track. That clear? Okay. Okay, great. So for this form, so we can show it works, right? As time goes to infinity, then the arrow B goes to 0. And you will see this form, right? It kind of makes sense, right? Yeah, see what it does. So it's just a constant, and then we add this. What is that? 1 over s, right? So what is 1 over s? It's integrator, right? So basically, integrator is kind of like, we amplify the impact of the error, right? So basically, it means that when the error is large, then we really want to, let it seen, in the input, and then we can get rid of the impact of the error, and then reduce the error, okay? So that's basically what this kind of filter does. Okay, and then we say, okay, so now everything we have been focused so far is when the input is just a carrier, right? It's A times the cosine omega CT plus the phase, right? It's just a carrier. However, in practice, for example, for the DSPSC signal right here, we have nothing to do with the FM or PM, right? We just want to see, okay, how we can apply PLL in general in practice, right? So now consider when the input is the DSPSC, okay? In this case, consider 2 cases. So one approach is the signal squaring, and the other one is the Costas loop, okay? And here is application of the PLL, and this one is another way to create a PLL so that we can do the coherent demodulation, okay? And this is the structure of the squaring. So basically, those are the procedures. So I'm not going to, give a detailed analysis of this again, but we did that in class. So basically, square it first, and then we have a bandpass filter, right? And then we have after limiter, and then we pass everything through a PLL here to get rid of all the higher frequency components. And after that, we do a frequency division by 2. Now, at this moment, we have the subcarrier, so which is the same as that with the same phase. Okay, so now if we have the same phase, then we can do a coherent detection, right? We multiply this guy and this guy. Then we pass everything through a low pass filter, and then we can get the original signal M of t. Okay, and so this is a Costas loop, and you can see that it's very similar. Again, so we did analysis in the class. So basically, after all this procedure here, right? So what we can get here is an error, and then after VCO, which is kind of integrator. right? So and then from here we can get we can get the signal that we're supposed to get, and then so basically with this multiplied that we can get a coherent demodulation, and here is where we can get the desired demodulated signal. Okay, and if you can see this structure, so it's very similar to kind of QAM quant, sort of like, right? Because here, is a cosine term, and here is a sine term, right? So this part can be think about the I branch, and this can be think about as the Q branch. Okay. Okay. Very nice. So. Okay, and this is what we did in the last lecture. So any questions? Okay, so if not, today we're going to finish talking about the analog communication. So basically, this is our lecture. Number 23. Okay, so our first topic is called super heterodyne receiver. And then we'll very briefly talk about two applications of FM. And then, if we have time, we'll give you an introduction of the sampling. So where sampling is the approach that we come from analog to digital. Okay? So yeah, let's start from the first topic. Okay. Let's see what is a super heterodyne receiver. Okay. So the motivation of this is as follows. Okay, so as we can see, for example, from the square signal squaring approach, as we have seen in the last lecture, right? We can see that so we need a bandpass filter, right? So this happens all the time, right? Because so normally we need a bandpass filter around the 2FC or FC. Okay, to get a signal out, and then we shift the signal back to the baseband to get the desired signal. Okay, we always see this kind of thing. Okay, but the problem is that it is it is not that easy to design a filter. That is have very high quality on any frequency point. Okay, it may be okay to design a filter on a certain frequency point, but we cannot say, okay, we design a filter that's tunable on any frequency. Okay, lower quality may be possible, but we cannot do that for high quality filter. Okay, then what should we do? Okay, so that's the motivation for the super heterodyne receiver. Okay, so when we cannot design the high quality filter on any frequency. Okay, what should we do? Exactly. Very good, right? So yeah, so far we have seen that, okay? So many things we have done is based on that we shift the frequency of the signal to somewhere, right? And shifting the frequency of the signal is pretty easy. Just multiply cosine in the time domain. Okay, then we can shift the signal around, right? So basically, what we do in practice is that we design a fixed frequency that has a very high quality, okay, for a certain frequency. And then when we receive whatever the frequency of the signal, we multiply cosine, right, and then shift that signal to the certain frequency band, and then we pass that through a low-pass filter, through a bandpass filter on that band, okay, and then we're fine, okay. So let's see whether this simple idea works or not, right? So that's basically the idea. There will be some problems, and we're going to see that later. Okay, so yeah, let's yeah, give you the definition of the super heterodyne. Superheterodyne was a fixed high Q bandpass filter at an intermediate frequency, or we call this intermediate frequency as IF. Okay, and the standard IF frequency is that as follows. So for AM, so that is 455 kilohertz. Okay, and for FM, so that's about 10.7 megahertz, and for the TVs, so that's about 38 megahertz. And those are the typical frequency range for the intermediate frequency. Okay, so basically it means that we're gonna design, we design a high quality filter basically around this point. Okay, and when we shift the signal, when we receive the signal, we're gonna shift the signal to this frequency range, to this frequency exactly, and then filter the signal out. Okay, so as we said, right, the idea is as follows. So the incoming signal is mixed with a carrier using an adjustable oscillator frequency. Okay. So this frequency is denoted by F, local oscillator, F, LO. Okay. So this LO is denoted for local oscillator. Okay. Okay. So now let's. So basically, this means that so our input have a center frequency around WC, right? So this is our input frequency, and after this mixing operation, our output is WIF, right? The center of the signal would be around WIF. Right? This is output. Okay, so now the key part is to design what this will be, right? So what this WLO will be. Okay. Any idea? Right. So basically, our input signal have a center frequency around WC, right? And then we mix that with the frequency like this, and then the output is WIF, right? So what should this look like?
Omega C minus omega IF.
Omega C minus, let's try it, right? So omega C minus omega IF. Okay. I think it's a good option. So any other options? Yes.
I think you flip it, IF minus omega c. Maybe.
Flip it? Okay. Let's see. Yeah, this may also work. Any other options? Any other options? Yeah, so basically, if we pick this option, so for the output frequency that we have is omega c plus this guy, and omega c minus this guy, right? So we'll have omega c minus this guy, then we'll have omega f, right? Yep, seems working, right? But the other part is 2 omega c minus omega f, right? And if we pick this guy, so when this minus that, we have a 2 omega c minus IF. When we this plus that, we have WIF. Yeah, it seems working, right? Yeah, there are some other options. For example, if WLO is, how about omega c plus omega IF? Would that work? Would that work? Yeah, actually, let's analyze this guy, okay, and see whether this guy works or not. Okay. Yeah, I think these two guys, do work, right? And so you can analyze this offline and see whether there's any problem on that, right? But this is typically what we use in practice. So let's give an analysis on this guy and see how it works. Okay, so basically the analysis of this guy is as follows. So let's assume our input modulated signal looks like this. So that's A times GT multiplied cosine omega c plus theta. Okay, let's assume that is our modulated signal. And then, so what we do is that we're going to look at ST multiply the carrier at W omega LO, right? So this multiply this, okay? Let's assume this is what is happening, right? And then, so we can see this guy equals to ST. Let's plug this in here. So that would be this guy. Okay, and again, so this is a cosine times cosine, so we have a cosine plus cosine, right? So let's use the trigonometric identity to get this. So we have a cosine of this minus that would be equals to WC minus WLO of T plus theta, and then we add this plus that, right? very good. So now let's see what we get. So this basically equals to as follows. All right, for the first term, so remember, omega LO basically we assume that this equals to what? Omega C plus omega IF, right? So this minus that would be equals to cosine minus omega IF. Okay, and then plus theta, right? And for the second part, so basically we have cosine, so we have omega c here, and we have omega c here. It's 2 omega c plus omega IF. There's a t, right? Then plus theta. Right, so this is basically what we get. Okay, and clearly, so this is the desired part, right? So for this part, so we're going to filter it out. Okay, so because here we just want to filter this kind of thing out, right? We don't need a very high quality bandpass filter to do that. Okay, and this part is what we want. Okay, and for this minus sign, the cosine doesn't matter. Okay, and so this is basically what we do. So any problems, right? So let's see whether we have any problems on that. Okay, so now let's assume that our signal looks like this. So this is input signal. We have minus omega c here, and we have omega c here. Okay, so after the shifting, let's see what does the signal look like. Okay, so basically, after the shifting, so what we're going to have is that, so yeah, let's see. So let's see, here is W minus the local oscillator, and here's omega of the local oscillator, right? So basically this will be shifting on this side, and this will be shifting around here, right? Because it's cosine, right? So now let's do it here. So we have one copy of the signal here. Yeah, it's not totally symmetric, right? You need to move this a little bit to make it symmetric, hopefully. Okay. Yeah. And then Okay, hopefully that works. And now, so what we want is basically this part, right? So that's is around omega intermediate frequency, okay? And the frequency component here is a minus 2 omega c minus WF, right? So this part can be filtered out. Okay. And for this part, so that's WF, right? And for this part is 2 times WC plus WF. Okay, very good. Okay, so basically remember, so what we do is that we shift this part here and then we shift this part here, right? By using the local frequency of oscillator, right? So is there any problems? That perfect? Right? Think in this way, right? So the frequency is normally not very clean, okay? So this is our transmitted or modulated signal, okay? So what if we have some other signal outside, okay? What will happen, right? Because when we multiply a cosine, it will going to shift everything here and here, right? Will that cause problem, right? For example, let's see. So let's see. Here is this guy, right? Yeah. Maybe. Yeah, I didn't draw it very well. So, yeah. Let's keep it the same here. Yeah. Let's see, how about we have a signal here. Okay. And the frequency component, so in the middle, so that equals to what? WLO plus WIF. Right? And that will be what? WLO is WC plus WIF and plus WIF again. So that equals to WC plus 2 times W or omega IF. Okay? What if we have a signal here? Maybe let's draw the signal in a different shape, right, to indicate so that's the non-desired signal. Okay? What if we have a signal here? Okay? And after shifting this guy by amount of WLO, so where that signal will be in this picture, right? So here is this guy. If we minus this by WLO, it will become WIF, right? That is here. Okay, this signal will be shifting here. Okay, and the WIF is our desired signal. Okay, so then there will be interference here. So that's not what we want. So that's a problem. Okay, and this signal is called image station. Okay, so that's not what we want. And how can we get rid of the image station? Yes?
You can maybe run through on the pass filter first.
Exactly. So, or we just run another bandpass filter with a certain bandwidth, but we don't need a very high quality of that, right? So we filter this part out. Okay, so we only need certain frequency, right? Because remember, we have a very high quality filter around here. Okay, so anything outside here doesn't matter, right? We only need, we filter out this part, and then we're fine. Okay. Yeah, that's basically the solution. So which is not, very hard. So basically, this means that we need a tunable band pass filter. Around WC to filter, things out, right? But we don't need a very high quality of it, right? So we just need to, keep our part and filter other part out. And for this part, it is pretty far away from our signal, right? So that's why we don't need a very high quality frequency of that. Okay, so. Okay, yeah, I think that is what I want to cover here for the super heterodyne filter receiver. So, any questions? Yes.
Is the IF frequency always greater than the carrier frequency used?
Oh no, carrier, no.
Okay.
Yeah, no. Here we didn't assume anything like the relationship between AF and carrier frequency. I think normally this will be lower than WC. Yeah, so here, maybe I draw it in a different way, but it's called intermediate frequency, right? Cannot be very high, right? Normally nowadays our carrier frequency is very high. So, okay, so now let's take a look at the applications. Yeah, so basically, this is a figure that I didn't draw, but you may want to take a look, right? So this basically is a procedure that we get rid of the image station, right? So we use an image rejection filter as I said there, okay? And then multiply this W local oscillator, and then pass everything through a high quality filter here around omega AF, and then we send it to a detector for the demodulation. It's very simple structure. All right. So now let's talk very briefly on the application. So basically, we're going to talk about two applications for the frequency modulation. So one application is the FM broadcast radio. So basically, the frequency band or frequency range for the FM broadcast radio is from 88 megahertz to 108 megahertz, okay? And the channel separation is 0.2 megahertz, like this. And so we have one at 88.1 and 88.3 and so on, okay? So that's how it works. And the delta F, in this case, hopefully still remember the delta F, right? So that's basically the highest deviation in the frequency, right? It doesn't mean the bandwidth, right? It's the highest frequency deviation. So in this case, it is 75 kilohertz. And so the message bandwidth now, because it's FM radio, right? Roughly speaking, the bandwidth would be 15 kilohertz. And so the bandwidth of FM here, so because this guy is very small, so we just ignore that. Okay, so this is the bandwidth of the FM signal. Okay, so that's called monaural signal. So what does this word mean? Monaural. Who heard of it? No? So it means mono, right? So, or it doesn't mean the stereo audio, right? Basically, two ears are the same. Okay. But for a better audio, when the two ears are different, so this is basically what we do. Right? When it's stereo, so basically means that the two ears have different signals. Right? But these two signals cannot be so different. Right? So basically what we do is like this. So we transmit. Oh, one thing is that we need to make it compatible with the mono audio, right? To make it compatible with the mono audio, basically means that we need to transmit a mono audio, right? And make it can be demodulated at the mono audio receiver, okay? And then we transmit the difference between the mono and the stereo. And if you can demodulate it, the stereo signal, and then you need to demodulate the additional part. Does that make sense? Okay, that's how it works. So basically, how we do this is that we add the left and the right together. Okay, so that's the mono part. Okay, and the stereo part is the difference between them, right? And we use L minus R here. Okay, and to recover the stereo signal at the end is that we just need to use this. We know this by M, we know this by D. We just use M plus D to get the left part, left ear. To use M minus D to get the right ear. Okay, and that's how it works. Okay, and then so this is basically the spectral signal look like, right? So this is the mono part, left plus right. So these are our FM signal. Okay, and then we transmit the difference using DSBSC. Okay, so this is FM, and this is DSBS. And in addition, so we use this part to transmit the palette signal, and that is a carrier to demodulate this DSBS. Right? Because we don't want the demodulator to be so complicated, we just transmit the carrier. Right? But the carrier here is 19 kilohertz, but we need a carrier of 38 kilohertz. So we need to double it in the receiver to demodulate this guy. Okay, that's how it works. Does that make sense? Right? Any questions? You can see that, in the practical system design, so it's slightly different compared to our theory, right? We need to, do lots of smart things to make it work in practice. Okay, yeah, this is what I said, right? So we need to use a palette signal at 19 hertz, k hertz, to generate the 38 hertz for coherent carrier for the demodulating the D channel, which is the DSBSC. Okay, so another interesting thing happening here is that, so we can mix the analog and the digital communication, right? So this is our FM signal. Okay, so this is what we just seen in the previous slide. Okay, but normally when we do the transmission, so we need some guard band. Okay, so the signal is not like very clean in the frequency, right? Not like, okay, so this is the bandwidth. As we have seen, right, for the FM signal, it will go on forever, okay? And those are small, right? Although those are small, right, it's hard to, use it to transmit anything, right? And, it's not like that. So what I mean is that, so others do not want to use, the so-called side lobe to transmit anything, right? Because there's still some signal going on. But for ourselves, so we can use it because those are some signal there already, right? So basically what we do is that we use a sideband to transmit some digital signal, right? Which is more robust to interference and noise. That is what we're going to cover next. Okay, so basically what we do here is that we use OFDM, so that will be our last topic, very last topic in this class, okay? Use the OFDM to transmit some high quality digital audio. So this audio can be improved version of the audio, or could be some information of the audio transmitted here, right? Like the meta information and so on. Okay, you can check it online. But the nice thing here is that we use the digital communication here, in compensate of that. Okay. Yeah. that is another very smart design in practice. Okay, and yeah, here, so this is another application. So we call that the US Advanced Mobile Phone System, or APMS. AMPS. So who heard of that? Yeah, probably you're so young for that, right? Yeah, I think I heard of it. You know, when I was learning, I think I started learning wireless communication in 2002. Okay, by the way, you were born? Like, really? You were born in 2003? Oh my god. Yeah, now I'm realizing I'm so old. Okay, anyway, so when I studied wireless communication, so I heard this a lot, right? It's kind of the very first, cellular system in the US first. I'm not sure whether it's in the world. Okay, so basically we use FM to transmit our voice. Okay, make phone calls, make phone calls and so on. Okay, in this case, so the channel is based at 30 kilohertz, and now we have a delta F of 12K. Okay, and now, so in this case, so the voice bandwidth is generally 4K, right? So, and as we're gonna see later, so if we want to sample that, we need the 8K. Okay, and now, since 4K compared to 12K, so it's not negligible. So we have to use, the Carson's rule to compute the bandwidth. It's 2 times 12 plus 4, so that's 32K, right? So that's the bandwidth for our signal. Okay, and how do we transmit is that we use a so-called FDD, right? So we talked about FDM before, frequency division multiplexing, right? This is totally different concept, right? Frequency division multiplexing basically means that it's one direction. When I transmit to you, I use different frequency component to transmit different messages, right? But FDD means the duplexing. So it's like, okay, so I use a frequency component to transmit to you, but you use another frequency band to transmit to me, but it happened at the same time. So we can talk to each other together, okay, which is great. Okay, so that's the concept of FDD. So it's called duplexing, frequency division duplexing. Okay, nowadays I think for 5G, so we use a lot of FDD still, but I think the better duplexing is called TDD, time division duplexing. Okay, and here is the frequency planning for the ANPS. So I think the important thing here is that you can see the starting frequency component, and here is the end frequency component for the reverse channel. Reverse channel basically means from the mobile phone to the base station. Okay, and forward means from the base station to the mobile device. Okay, and you can see the difference in frequency between here and there is like 869 minus 824 is 65 megahertz. Okay, and all those are the channel number. Okay, you can see different band has a different channel number. Okay, AB basically means for certain range of the channel number, so you call that A, and for the other for some others we'll call that B. Okay, and for this, I think this is a second generation or first, I don't recall, but anyway, the amps stopped serving in 2008, right, which is not too long ago, and the last one was turned off in 2011. Okay. So yeah, another thing here is very important is that so this is a cellular system. So by cellular I mean so the system. So consider so this is a cell, right? Within the cell, let's see here is the base station. Okay, and so basically what we do is that we cannot let only one frequency of one base station transmit and everything else keep silent, right? That is very inefficient, right? So what we do is that, so we can say this, and that use the same time and the same frequency, okay? So because the distance between this and that is far enough, then we're okay, right? So basically what we do is that we take a number of it, and if each cell have the same number, then we can let them transmit all together in the same frequency band, okay? So this is very important. Okay. Yeah, it's called 7-cell reuse pattern. Yeah, by the way, so this is called frequency reuse, okay, or spatial reuse, right? So this spatial reuse is very key for, that we can improve throughput even for the modern wireless communication system, okay? And nowadays the difference compare the current technology and this technology is that we make the cell become smaller and smaller, right? Make the antenna more directional and make the cell become smaller and smaller. So it's called femtocell or picocell, whatever. So that's small cell, right? If we make the cell smaller and smaller, and then if we keep using this pattern, it means that we can transmit more within a certain area, right? So that's basically the idea. Okay, yeah, and I think that's all I want to say for the applications. And from the next lecture, so we're going to answer those kind of questions, right? So we're going to see how we can analog to digital and why we want to do digital communication. Okay, yeah, thank you so much. See you next time.